that. All right, so in 10.3 today, we're looking at rotations. So we're going to define and perform some rotations given the center and angle of rotation, or given two intersecting lines of reflection. And then we're going to find the center and angle of rotation from a given pre-image and image, and use coordinate geometry to find image points after a rotation. We're actually only going to do the last one for our study of rotation today. Okay, so rotation. How would you describe a rotation? Like you've been talking about rotation. What was it? Turning. Okay, rotation is a turn. Okay, so in this case, a little bit more mathematical description is a transformation defined by its center and the angle of rotation. So we still have that turn. Okay, so the angle of rotation is x to the power of 0, and your center is c. Okay, it says such that c prime equals c. What on earth does that mean?
Oh, is C prime that's the reflection?
Okay, what's the C represent?
The central.
The center. Okay, but that C is the center. So the center
is the actual curved part right at the end.
The actual curved part at the end. Okay, so C is the center. No. Okay, C represents its center. Okay, so it doesn't matter. It's saying the center of our image, C prime, is the same as the center of our pre-image, right? So if we look here, this is the center of either one of them. It's the same center. Okay, so they have the same center. Then part 2 of this is every point P is mapped onto point P prime. Okay, so if this was P, let's see, do they have it? Okay, yeah, so see they have here, these 2 points here. They map the same distance. It's still that 60 degrees. If this is P and this is P prime. Okay, they're mapped 60 degrees. If our central angle, or our center, and we're doing a 60 degree, they're 60 degrees away from each other. Okay. So then we say such that C P prime, so that length is equal to the same length as C to P. So the length from C to P is the same as the length from C to C prime, or P prime, pardon me. So those lengths are the same. And the measure of angle PC P prime, so the measure of this angle from here to there, right, is that angle of rotation. It's x to the power of O. Huh? Oh, it is degrees. I'm sorry. X degrees. Sorry, in my last class, we've been working a lot with exponents, and I have that on the mind. All right, so then it says clockwise rotations are indicated by x is greater than 0. Or counterclockwise rotations, pardon me, are indicated by x is greater than 0. And then this kind of got out of order, which means counterclockwise rotations are described as positive, where clockwise rotations are indicated by x is less than 0, so they're negative. Yep, clockwise rotations are described as negative. We can have a magnitude of rotation, so that's the measure of the central angle is defined by a pre-image point, the center of rotation, and the point's image is our magnitude of rotation. So again, it's just the measure of the central angle. And then identity transformation is a fun one. What's the identity law of addition? Do you know? No, the identity law of addition. No, it has nothing to do with this, except it has identity. Identity law of multiplication. Anybody? Well, probably, but that kind of defeats the purpose. Okay, the identity law means no matter what, like whatever you're doing to this, what you do to the number keeps the same number.
So like 5 times 1.
Yeah, so the identity law of multiplication is any number times 1 is that number. In addition,
it's anything plus 0 then.
anything plus 0 is that number, okay? So then the identity transformation is, it's just a mapping of the preimage back onto itself so that the preimage and the image are the same. Okay, so it's keeping the same identity. The preimage and the image have the same identity. It didn't move. They're the exact same. So it could be that we do a 360-degree rotation. If you rotate something 360 degrees, it's going to be in the exact same position it was. Or it can be a composition of rotations, like a composition of a 90 and a 270-degree rotations. And it's going to map it back to the exact same thing that it was. So its identity didn't change overall. Okay. Okay. Then we have some counterclockwise rotations about the origin. So our center is the origin here. Because we're just focusing on the geometry aspect of it. All right. So when we have a 90-degree rotation, this is what happens to our coordinates. So describe that to me. What happened from P to P prime? No, XY is not the point of origin. It's like XY is up here. Like the origin is our center.
No, like the original P.
The original P?
Yeah.
We don't know the coordinates themselves. But we do know there's an X. We're saying they're X and Y. So what happens when we map P, which is XY, to the P prime? What happens to our X and our Y? Did they both go negative?
No.
Okay, then that's not what happened.
One went negative and then they switched places. I don't know.
Okay, you do know. So X and Y switch. Okay.
Y goes negative.
All right, and Y goes negative. Again, this is a 90-degree turn. Okay, what happens to our coordinates in a 180-degree turn? They both go negative. Do any of them switch?
No.
Okay, so they both go negative. Okay, and in a 270-degree turn, so X and Y switch, X goes negative. Perfect. Okay, because the reason we're going to use that, or this is helpful for us, unfortunately you have to memorize that to be helpful, but we're going to find the coordinates of the images of the vertices of triangle FGH after 270-degree rotation about the origin, and then we want to graph F prime, G prime, H prime. So we're doing a 270-degree rotation. So that's when our XY, right, is going to be X and Y switch. So we're going to have YX, and then we said our X goes negative. All right. Let me pause so we can pray, and then we'll continue in just a second. Tu padre?
Huh?
Tu padre? Like your father? Okay, we'll have to share on that time. Okay, so then what are the coordinates of F? 1, 2? Okay. So 1, 2. So what are the coordinates of F prime going to be?
Would it be 2, negative 1? Yeah, 2, negative 1.
Okay. Right, because they switch places and then our X goes negative. Good. All right, so what are the coordinates of G?
0, 0, 3.
0, 3. You guys agree with that?
No, whatever he says is wrong. Yes, that's right.
Okay. So what are the coordinates of G prime?
Would it be 3, 0?
So 3, 0, right? Because we can't have a negative 0. Doesn't happen. All right. What are our points of H?
3, 2.
Negative 3.
Negative 3. -2, okay. So then what about
2, 3.
h prime? So -2, and then for -3, right, our x value to go negative, it's going to be a positive in this case, right? It's a -3. Good. And then you're ready to graph it. Like, that's it. We had to find the coordinates of the images, and then we did the new coordinates of the image. So we did the pre-image and the image. Now we're ready to graph it. So 2, -1 is f prime. 3, 0. 1, 2, 3 is g prime. And -2, 3. 1, 2, 3 is h prime. So this was a 270 degrees rotation. Was this clockwise or counterclockwise? Counterclockwise, right? If it's positive, it's counterclockwise. Or what's another way we could describe this rotation? Instead of saying it was 270 degrees, or it'd be -90 degrees. Or we would say which was the clockwise rotation, right? So there's a couple different ways we can look at those. Very nice. You're welcome. All right, you guys got that all down? Do you guys have it all down? You don't have it all down? I'll pause it. Well, we'll continue to pray that it works out. All right, so example 4 then. We have the giant Ferris wheel at the Cedar Point Amusement Park in Ohio contains 36 passenger cars. How many degrees must it rotate before the next passenger car is loaded? How'd you get that?
Because it's a circle, and a circle has 360 degrees, and there's 36 passenger cars.
That is correct. Yeah, very nice. A little too easy, right? A little too easy. Okay, so if it takes 20 seconds to unload and load a car, how long does it take for a newly loaded car to rotate to the top of the wheel? 136 feet in the air. You're okay. Takes 20 seconds to unload and load a car. How long does it take for a newly loaded car to rotate to the top of the wheel? What was it?
Is it counting in the 20 seconds?
Mm-hmm.
We will count in the 20 seconds. So let me move this up a little bit so we have a little bit more room to work. I'll leave that there.
360 seconds.
360 seconds? What do you mean? Well, no, I just feel like 360 seconds, like, what do you mean? How did you get that?
Because, so to get to the top,
Uh-huh.
and it's already at the bottom, you don't really have to worry about any of the other cars. So it's only going 180 degrees.
Okay, so let me draw a picture here. My really terrible Ferris wheel. Okay. So he's saying we have a car down here at the bottom. Okay, and we want it to go to the top, and when it will get here.
So you would
And
just
that's
multiply
180 degrees.
18, because there'd be 18 cars by the time you go up there that need to be reloaded, including yours.
Okay, so you're saying that this is going to reload 18 cars?
Yeah.
Okay, what was the question, Justice? No, go ahead. It's a good question.
Because it's half of the Ferris wheel that I'm going to.
Okay, good, because they told us there were 36 cars, right?
All these questions are going together?
Yeah, like, because it was the question, and then it was A and B. So there's 36 cars total. Good. So in half, in 180 degrees, there's only 18 cars. We've divided that by 2. Nice. Okay.
And then you just multiply 18 by 20.
Okay, and so then So it's taking, because it takes 20 seconds to load and unload a car.
To load and unload?
Mm-hmm. So if it's taking 20 seconds to load this car and 20 seconds to load the next car, to load 18 more cars, we're going to take 18 times 20, and you got 360. But this was 18 cars,
Loads and unloads.
right? 18 loads and unloads. Slash unloads.
Oh, so that's
And this
that's
is
the amount of
20
seconds that's
seconds.
Yeah.
So there's 360
seconds.
seconds.
And loads and unloads, but you still got to figure out like how many seconds are between each load and unload.
No, I think it's like 20 seconds between each car, essentially.
Oh.
Like, because a lot of times, bigger Ferris wheels like that, they have a big platform. And when you hit the platform, like you're supposed to be walking off of it and out. And the next people are walking, as it's moving through that platform, the next person is walking on it, group.
Oh, so it doesn't stop.
So it doesn't stop. Yeah, it's like a, it's how it is at a lot of the big
So in
ones.
Florida, we had like there's a huge one and it stopped completely like every time because he would like launch it back.
It would lurch back and forth. Okay, and like older ones do. A lot of the new ones, it's very seamless. Like they have a really long platform, and so there's a line getting off and a line getting. I mean, like the people getting off will get off on one side.
Screw up. I'm sure because it goes slow.
Yeah, it does go slow.
Like time it perfectly.
Yeah, and so but like the people getting off get off on, you know, they're walking out the left side, and the people walking on are coming in the door on the right. Like there's a door on both sides, and so it's pretty seamless. And even if yeah, and people have wheelchairs and they can just roll them right on because it slides along. Again, this platform is designed for that, so you can roll them into it right off the platform and everything else. They're pretty awesome when you get to do it. And then it's nice that it doesn't jerk and lurch 36 times, you know, like as you're going around. Like, this is a boring ride. Okay, so let's see. Well, let me look back at the question. So it takes 20 seconds to load and unload a car. How long does it take for a newly loaded car to rotate to the top of the wheel 136 feet in the air?
That feet doesn't matter.
That feet doesn't matter. Nope. Although 360 seconds seems like a weird way to measure something. Like, I would think we could convert that to minutes. Divide by 60? Okay. So 360 seconds divided by 60 would give us, what'd you say, 6? That's correct. Good.
Okay, but like, in my defense, it didn't say what to finish it out as. Because it started in seconds. So
it didn't. This is true. Like 360 seconds is also correct. That's why I looked back at the problem and it doesn't say, but that's why I was like, well, you know, if you have that many seconds, you could convert it to minutes. So let's try that. Is there another way you could have solved this?
This probably wasn't the way that you wanted us to solve it.
It's not the way the book solved it, but it's not a bad way to solve it. It's fine.
The book kind of sucks.
Sometimes.
A lot of their solving is like dumb.
Well, a lot of, so my only thing is that, and I mean, like the reason you could solve it differently is in these types of problems where we have a problem and we have an A and a B, they usually go together. You can build off of them. And I left A up there as a way for you to be like, oh, okay, how could I use this? Because A said, how many degrees must it rotate before the next passenger car is loaded? 10 degrees. Well, and you found that this was 180 degrees to get to the top. So 180 degrees divided by 10 degrees would have given you 18, which is what you already had, the 18 cars. It was just a different way to get 18 cars. That's all I was going at. Like the way you calculated your 18 cars was the only change that I would say, a different way you could look at it. Otherwise, you are free to get started on your homework.